In today's video, we'll explain what a compact star is and the different types that exist in the cosmos. We'll discuss these fascinating astronomical objects, such as degenerate stars like white dwarfs and neutron stars, whose stability is ensured by quantum phenomena like degeneracy pressure, which counteracts the force of gravity. Additionally, we'll explore other types of stellar remnants, such as black holes, which represent the complete collapse of a star's core, with no known process capable of counterbalancing gravity. As many of you may know, stars remain stable thanks to a balance of forces. On one hand, there's the outward pressure exerted by nuclear fusion processes in the star's core, and on the other, gravity pulls inward due to the star's massive weight. While this balance can last billions of years, it doesn't last forever. When stars exhaust the nuclear fuel they fuse to produce energy, they collapse under their own weight, as gravity no longer has an opposing force. For most stars, when this happens, a very dense and compact stellar remnant forms, also known as a compact star. These remnants no longer produce internal energy, but typically radiate leftover heat from their collapse for billions of years. Without that nuclear energy source to counteract gravitational collapse, these dead stars are compressed to the maximum extent allowed by the physical laws of our universe. Furthermore, depending on the mass of the star from which they originated, the gravitational collapse results in the formation of different types of compact stars. For example, when a star with less than about 10 times the mass of the Sun runs out of nuclear fuel, it expels a large portion of its outer layers in a planetary nebula, while its core collapses, leaving behind a stellar remnant known as a white dwarf. Our own Sun will become a white dwarf when it runs out of fuel. In fact, this is a stage of stellar evolution that 97% of known stars will go through, as white dwarfs along with red dwarfs are the most abundant stars in the universe. White dwarfs are compressed so tightly under gravity that atoms are forced closer together, severely restricting the movement of electrons. This gives rise to what is called electron degeneracy pressure, which prevents further collapse into an even smaller and denser volume. To give you an idea, our Sun currently has a volume about 1.3 million times greater than Earth's, but a white dwarf can be so dense that a mass similar to that of the Sun would be compressed into a volume comparable to Earth's. At such high densities, electrons are affected by Heisenberg's uncertainty principle and Pauli's exclusion principle, forcing them to move at very high speeds, which generates the so-called electron degeneracy pressure. This is what effectively halts the further collapse of the star into higher densities and keeps this stellar remnant stable. Typically, 99% of white dwarfs are composed mostly of carbon and oxygen, which are the byproducts of helium fusion. However, in most cases, their surface also contains a layer of compressed hydrogen and helium that forms the white dwarf's atmosphere. Additionally, newly formed white dwarfs have extremely high temperatures, ranging from 180,000 to 360,000 degrees Fahrenheit at their core. However, since they don't produce energy, they gradually cool down, which is why they have very faint luminosities. In theory, white dwarfs will eventually cool to the point where they no longer emit detectable radiation, ultimately becoming black dwarfs, cold, invisible bodies in space that no longer emit light or heat. However, the cooling process is so slow that the age of the universe since the Big Bang is too short for any black dwarfs to exist today. Likewise, for electron degeneracy pressure to counteract the gravity of a white dwarf, its mass cannot exceed the Chandrasekhar limit, which is 1.44 times the mass of the Sun. Currently, we know of white dwarfs with masses ranging from 0.17 to 1.3 solar masses, though the vast majority fall between 0.5 and 0.7 solar masses. Additionally, the estimated average radius of white dwarfs is very close to Earth's, which is the size most of them have. However, in some cases, white dwarfs can increase their mass by pulling in additional matter from nearby stars, which is common in binary star systems. When this happens, and the white dwarf's mass increases as it accretes matter from its neighboring star, if the white dwarf reaches the Chandrasekhar limit of 1.44 solar masses, the electrons are no longer able to counterbalance gravity. This leads to a sudden collapse, triggering uncontrollable thermonuclear fusion throughout the star, resulting in an extremely bright explosion known as a Type 1a supernova. This process typically completely destroys the white dwarf, scattering its material into a nebula. Now, setting white dwarfs aside, we move on to another type of compact star, neutron stars. These remnants form from the gravitational collapse of a massive supergiant star after it explodes as a supernova, compressing the core beyond the density of a white dwarf. These stellar remnants form from stars with even greater mass, typically between 10 and 25 times that of the Sun, as their name suggests. Neutron stars are primarily made of neutrons, since most of the electrons and protons in the star's matter combine to form neutrons under the immense pressure and heat exerted during the collapse of such a massive star. Neutron stars also typically have an iron crust, and with the exception of black holes and some hypothetical objects like white holes or quark stars, neutron stars are the smallest and densest known stellar objects. Neutron stars usually have masses between 1.1 and 2.3 times that of the Sun, as the rest of the progenitor star's mass is scattered into a nebula after the supernova explosion. In the case of a neutron star, all the collapsed mass is compressed into an object with a radius of only about 6 to 7.5 miles, much smaller and denser than white dwarfs despite being more massive. To give you an idea of the density, it's roughly equivalent to compressing the mass of a Boeing 747 into the size of a grain of sand. This incredible density gives neutron stars extreme surface gravity, about 100 billion times stronger than Earth's. One measure of this immense gravity is the fact that neutron stars have an escape velocity of over half the speed of light. So, if we wanted to leave its surface in a spacecraft, we'd need to reach this astounding speed. Despite their immense density, neutron stars avoid further collapse due to a phenomenon described by the Pauli exclusion principle. This principle states that two neutrons, or any other fermionic particles, cannot occupy the same space and quantum state simultaneously. Similarly, just as the maximum mass of a white dwarf is limited to 1.44 solar masses by the Chandrasekhar limit, the theoretical maximum mass of a neutron star is constrained by the Tolman-Oppenheimer-Volkoff limit, which is estimated to be between 2.1 and 2.3 solar masses. This uncertainty arises due to the complexities surrounding the nature of matter at such extreme densities. Additionally, during its formation, as the star's core collapses and becomes smaller and denser, its rotational speed increases due to the conservation of angular momentum. As a result, newly formed neutron stars can spin up to several hundred times per second. Some neutron stars also emit beams of electromagnetic radiation as they spin, and in these cases they are known as pulsars. It is believed that pulsars emit radiation primarily from regions near their magnetic poles. If the magnetic poles are not aligned with the star's axis of rotation, the emission beam sweeps across the sky. Seen from a distance, this creates pulses of radiation from a fixed point in space, making them similar to cosmic lighthouses that could potentially be used for navigation in interstellar travel. For example, the fastest known spinning neutron star rotates at 716 times per second, or 43,000 revolutions per minute. Another type of neutron star is the magnetar, named for its incredibly strong magnetic field, which is about 1 trillion times stronger than Earth's magnetic field. Magnetars form when the core of a star collapses into a neutron star, and its magnetic field intensifies dramatically due to the conservation of magnetic flux. Having a linear dimension increases the magnetic field strength by 4 times. It is believed that when the spin rate, temperature, and magnetic field of a newly formed neutron star fall within a certain range, a dynamo mechanism can convert rotational energy and heat into immense magnetic energy, creating a magnetar. It's currently estimated that roughly 1 in 10 supernova explosions results in the formation of a magnetar instead of a neutron star or pulsar, making magnetars less common. In addition to their strong magnetic fields, magnetars differ from other neutron stars by rotating more slowly. Most of them take between 1 and 10 seconds to complete a full rotation, while an average neutron star spins in less than a second. Furthermore, the active lifespan of a magnetar is relatively short, as their powerful magnetic fields weaken after about 10,000 years, causing them to gradually lose their X-ray emissions, though they still remain as neutron stars. Moreover, starquakes on the surface of a magnetar cause significant volatility in the stellar remnant and the surrounding magnetic field, often producing intense bursts of gamma rays, which we've been able to detect from Earth. Magnetars are, therefore, the most powerful magnetic objects detected in the entire universe. Their magnetic fields would be lethal, as they distort electron clouds in the atoms of any living being that approached too closely, making the chemistry of known life forms impossible in their vicinity. It is also estimated that if a magnetar were located at the same distance from us as the Moon, it could erase the magnetic strip information on all credit cards on Earth. Finally, in addition to white dwarfs and neutron stars, whether they are pulsars or magnetars, the only other type of compact star we currently have evidence for is the stellar black hole, which usually forms through the gravitational collapse of a supermassive star with more than 30 times the mass of the Sun. When these gigantic stars exhaust their nuclear fuel, a supernova occurs, followed by the gravitational collapse of their core within milliseconds. During this collapse, the escape velocity at the surface of the core rapidly approaches the speed of light. Once the escape velocity reaches the speed of light, no matter or energy can escape this stellar remnant, confirming that a black hole has formed. The minimum estimated mass for these stellar black holes is around 3 solar masses. In addition to forming through stellar collapse, we also know that a stellar mass black hole can form from the merger of 2 neutron stars. On the other hand, the largest known stellar mass black hole weighs in at 80.3 solar masses, having formed from the merger of 2 other stellar black holes. Moreover, there are no known processes that could produce black holes with a mass smaller than several times the mass of the Sun. If such black holes exist, they might be primordial black holes that formed in the early universe. Although, theoretically, black holes of any mass could exist, we also know that supermassive black holes exist at the center of nearly every galaxy, some with billions of times the mass of the Sun. However, it is unlikely that these formed from stellar black holes that absorbed more mass or merged with others. Instead, they likely formed through extreme events in the early moments after the Big Bang. According to classical general relativity, when a stellar black hole forms, a gravitational singularity is created. Occupying an infinitely small point, it's possible that gravitational collapse halts at a size comparable to the Planck length. But at such tiny scales, no theory of gravity has been developed to predict the physics that may occur. This singularity has such colossal gravity that nothing can escape from it once it crosses a certain distance, including light itself. Surrounding this singularity is a boundary in spacetime known as the event horizon. Events occurring on one side of the horizon cannot affect an observer on the other side. For example, light emitted from within the event horizon could never reach an observer outside of it, but for an observer inside, light from outside could still enter until the observer nears the singularity. However, due to the extreme curvature of spacetime, the perception of surroundings and the passage of time would change drastically and be subject to relativistic effects. Since all light and matter are trapped within this event horizon due to the immense gravity, the black hole is truly and completely black, except for a faint radiation known as Hawking radiation. Nevertheless, when black holes are devouring mass from other stellar objects or clouds of gas and dust, an accretion disk forms around them. This disk consists of matter spinning at immense speeds as it spirals toward the black hole, causing the temperature of the matter to rise to millions of degrees. This generates a strong emission of X-rays, which scientists have used to detect astronomical objects that do not emit radiation on their own, such as neutron stars or black holes. Furthermore, a black hole can only have 3 fundamental properties: mass, electric charge, and rotation. It is believed that all black holes formed in nature rotate due to the conservation of angular momentum from the star that produced them, similar to what happens with other stellar remnants. Setting aside stellar black holes and the other compact stars we've discussed, there are also other theoretical objects whose existence has not been proven, meaning they remain hypothetical. Among them are quark stars, which would form when neutrons are exposed to certain extreme conditions of pressure and temperature, causing them to break down into their constituent quarks, creating a star composed of quark matter. In this scenario, the star's matter would be compressed even further than that of a neutron star, becoming denser, but instead of collapsing into a black hole, the star may stabilize and remain in this state indefinitely, as long as it does not accumulate enough mass to trigger a complete collapse. Other hypothetical compact stars include preon stars, which are composed of a hypothetical group of subatomic particles called preons. These stars would have immense densities, possibly existing as an intermediate state between quark stars and black holes. There are also Q stars, sometimes referred to as gray holes, electroweak stars, or boson stars. However, since the existence of these types of theoretical stars has not yet been proven, we'll save a more detailed discussion of them for a future video to keep this one from getting too long. That brings us to the end of today's Via Doctis video. If you enjoyed the video, don't forget to like and subscribe to the channel. Thank you for watching, and we'll see you in the next one.